something.
I think I've got good chances.
Do you have new information? Or?
I mean, I'm still talking to like Verity and like Eric about everything, and I've been looking at a whole bunch of like fellowships. There's like the Marie Curie fellowship is the only European one that I can apply for right now, but I have to resubmit my paper, which means rewriting my paper. So I'm not sure. I'm also trying to go to Monkey Island now.
Oh yeah.
Yeah, Kelly's going, and she wants me to take, or she wants to take 3 undergraduates. Chances like I can go if we can find money. Which would be cool. So they're actually studying basically the red frame effect for female rhesus macaques, which is very interesting for mating strategy. Which is not interesting.
He did say yeah, because I'm not gonna worry until he.
How are you guys all doing? I guess we'll start in a little bit because I think there's probably still people coming in. One person just asked me, "Oh, I haven't heard from you about my project. Does that mean there's a problem with it?" The problem is me not having gone back to everybody about their projects yet. So if you haven't heard, there's many of you, not all of you, have not heard back from me about your projects yet, and that is not a bad sign from your end. It's a bad sign for me not having done it all yet. But I thought they all sounded like very good ideas.
Just not.
Is this visible? It's kind of visible. Was anybody so taken by the joy of Matlab and exploring slowly patterns that they downloaded this and tried playing with it? Is it? No worries if you haven't, because that's what we're going to do now. So Dan has been videotaping and putting up these things on YouTube. They're all under the same username. Let's see if we can find them. Has anyone like missed any of the classes and watched one on YouTube? Is that, I don't know if this is actually a helpful thing. No, I don't seem to even have an internet.
It's helpful.
Yeah. Is the sound quality okay? Can you actually like hear it and see what's going on now?
From the ones I watched in the beginning, yeah, it was okay.
Okay. Well, this is all thanks to Dan and his fine work. I don't think any of them have gone viral yet.
Which is good.
Oh, yeah. Yeah, no, it would be weird if that happened, but is everyone here, more or less? I don't know. It looks like a thinner attendance than usual, but that doesn't mean there's more people coming. Okay, so the aim for this one, so we started exploring a little bit last time, kind of conceptually what's going on in the Kamitani and Tong paper, and then we started exploring a little bit in a kind of concrete computational way, not their actual data, but a kind of simulation of the kinds of processes that might be going on. And one advantage of actually being able to explore a real simulation of it is that you can, for instance, look at look at some of the mechanics of how you would do a simple decoding. And that's something that we've not really looked at in actual computational detail yet. We just kind of talked about it. And as you'll see, it's actually, at least for a kind of simple case, relatively straightforward. But my hope is that it'll be kind of interesting and useful to just see how would one actually program such a thing, because we'll be doing more of that as the class progresses. So this is kind of one of the first forays from the more purely conceptual end to the kind of nuts and bolts of, well, how would you actually do something like this? And although this is just with simulated data, the processes are extremely similar to what you would do with real data. So this is going to be kind of partly Matlab tutorial, partly kind of basic classification tutorial, partly kind of exploring more what kinds of things might be going on in this data, well, in the simulated data, what would be the effect of noise, things like that. So, so did anyone, I kind of asked this before everyone was in the room, did anyone try exploring this stuff on their own a little bit? Or no worries if you haven't, I'm just curious as to whether the availability of these MATLAB things is actually a helpful thing. Okay, well, we'll go through it now. So the, let's just kind of recap conceptually a little bit kind of where we're at. So, would anyone like to give a kind of broad brush description of why one might expect that different voxels might have slight sensitivities to different orientations?
Depends on which region of the cortex it's imaging.
Right, very good point. Some parts of cortex contain, some brain areas contain neurons that are highly sensitive to orientation, and others, such as primary visual cortex, which is where they were looking at in the study. Other areas are sensitive to all kinds of stuff, maybe like high level visual features, but not necessarily so sensitive to these kind of lower level things, like just which way is an edge pointing. And suppose you have, and then the problem is that even within primary visual cortex, you've got these great big, coarse-grained voxels containing lots and lots of cortical tissue, and within that tissue there's lots and lots of different orientations, all neurons sensitive to all kinds of different orientations. But this approach kind of relied upon this idea that even despite the fact that there's all kinds of different orientations sensitive tissue within a given voxel, the end result might be that some voxels might be have a slight preference for one orientation or a slight preference for another orientation. Would anyone like to give a kind of mini summary of why all the voxels might not end up looking just exactly the same as each other? Yeah.
Well, orientation columns aren't evenly distributed, right, depending on their orientation necessarily.
Right.
Depending on.
Exactly. So basically, you've got this kind of regular grid-like thing, namely the grid of voxels, but you've got this kind of uneven, irregular, swirly-whirly pattern of orientation columns that the big coarse voxels are sampling, and a kind of lucky consequence of that is that different voxels are going to sample, just by chance. Some of them are going to sample a bit more of one orientation, some are going to sample a little bit more of another orientation. So then if you pool information across lots and lots of voxels, you might be able to exploit some of these kind of just small individual differences, small voxel individual differences in sensitivity, and overall get a decent answer. So so let's have a little look at as to how you would do that computation. So one of the aims of this class is really to kind of understand at a conceptual level how some of this decoding might be happening, but also be able to implement it, or implement some of it. And so this is going to be, I think really our kind of first look at doing some of the actual implementation. But this is a very simple implementation, but it kind of shows the idea. So on Tuesday we looked at just kind of we just made some of the figures and looked at how they actually kind of look similar to the types of pictures that were made in the Boynton commentary. I don't think it's really that important for you to kind of go through exactly how we made the figures, although I'll just kind of show it to you briefly, just as a way of doing, because it's useful to know how you just kind of do stuff in Matlab. But we're going to concentrate more on the decoding part. But I think it's just kind of a little bit interesting to look at the process of making the figures. So one of the reasons why, I mean, Matlab is not the only game in town by any stretch of the imagination for doing fMRI analysis, but it happens to be a quite well-suited language for it. And so, this package that we were using in the computer lab the other day, SPM, is written entirely in Matlab, for instance. It happens to be quite well-suited because MRI images are just big grids of numbers. 3D grids typically, 3D matrix being the kind of jargon term for a grid of numbers. And everything in Matlab is by default a matrix, a grid of numbers. Now it might be a special case, it might be just an individual row or column of numbers, so that would be called a row vector or a column vector. Or it might be a two-dimensional one, such as, say, a slice. An MRI a slice would be a two-dimensional image. Or it might be a three-dimensional, or you can even have arbitrary number of dimensions. If you had, say, lots and lots of different types of information you wanted to all combine together. So this is how you would start making a grid. So if you say, okay, I want it to have 300. So these are not voxels in this case. These are like the little pixels that make up what. So this is a 300. Oh well, this actually becomes okay. It gets cut down actually. I'll show you why in a minute. But we're going to have like a 200 by 200 kind of pretend visual cortex, and we're going to turn it into. We're going to sample it by a 4 by 4 grid of voxels. So. So if you want to make a random grid of numbers, then you can just use this command rand, and it will make just random numbers. In this case, the default is just Gaussian distribution centered around 0. So typically angles are called theta. So this is this thing here is 300 by 300 set of random numbers, and then we're going to turn them. Instead of them going between the range of, say, -1 and +1, we're going to make them span a range of angles. Have all of you encountered the concept of measuring angles in radians? Radians. So typically we do angles in degrees, and it's 360 degrees obviously in a circle. It turns out that it's mathematically more convenient to use a much bigger unit, which is like 57 point something degrees, called a radian, which is at such that it turns out there's actually 2 pi radians in a circle rather than 360 degrees in a circle. And it's actually because if you're going to do differentiation, it turns out to be more convenient. But anyway, that's just how these things are often implemented. So we're going to blur stuff with a Gaussian. Lots of things in science in general, but especially in MRI, involve using Gaussians. Has everyone encountered the concept of a Gaussian? It's often called a normal distribution. In fact, well, if you do, they crop up all over the place. And there's actually kind of interesting mathematical reasons for why they crop up all over the place. In this case, we're just going to use it for blurring. So we're going to make a Gaussian, and the basic equation for a Gaussian is this thing of e to the minus s squared plus y squared. This is basically just the distance from the center of your Gaussian here. Is my little mouse showing up here? Can you see that a little bit? It's not very high contrast there. So this is this ends up being just a big blur. saying it's high in the middle, a kind of two-dimensional bell curve of high in the middle and low at the bottom. So if you convolve everything with that, remember we were talking about convolution for HRFs. So if you do image processing, including MRI image processing, you, instead of doing what we were doing was a one-dimensional convolution, if you have this time series and every onset time gets convolved by this kind of wave-shaped HRF, in image processing you typically have a two-dimensional Gaussian and you would convolve with that. So that has the effect just of blurring everything. So so it's actually very easy to do that in Matlab. You just as we use the command conv for one-dimensional one, there's a thing called conv2 for a two-dimensional one. And by the way, often if it turns out, often in MATLAB, as you kind of learn to program a bit, you'll be kind of thinking, I wonder if there's a function that does blah. And I bet there is one, but I don't know what it's called. And that happens a lot. Well, Google is often your friend there, but there's also a useful command within MATLAB called look for. This is actually a very useful MATLAB function. So if you say like, so you just do look for and then you type a few letters from the name of the thing. You know, I want something to do with convolution, but I don't really know what it's called. So I'll say, okay, look for something that has where the command or the description of the command has the words conv in it, letters conv in it. Oh, there's a lot of stuff with convolution in it. Okay, and then you get because it's all the stuff with convert in it. Okay, so you can get too many hits. It's just like Google. Okay, let's try convol. Okay, it should get less stuff. Okay, so you can see there's loads and loads of things with convolution in it, including lots of SPM functions. Now it's anything on your path actually, including my little kind of tutorial that we went over. But somewhere in there will be, there you go, conv2. Okay, the two-dimensional convolution. And in fact, you can even do n-dimensional convolution if you want to. So that's the kind of useful thing for finding out what exists. So anyway, so we blur our map with by convolving with the Gaussian. This is just a useful, although it's not particularly important for right now, it's a very useful thing to do in general. Often you'll find yourself wanting to do something like that. Then we do a little bit of kind of fussy stuff to do with the fact that we're dealing with angles. I wouldn't worry about that for right now. The main thing that when you're dealing with angles is to make sure that your program treats -1 degree and 361 degrees as the same thing, because it loops around. So we do all that, and we end up, we've made our random orientation. So that's figure 2. So this is the thing that looks amazingly like a visual cortex map. Now this does not at all imply that the visual cortex map is actually made by blurring random orientations. It just means that if you do blur random orientations, you get something that looks very similar to it. What's actually probably the case is that something sort of computationally related happens. So if you think, what is blurring? Okay, blurring is kind of mooshing something in a little bit with its nearby neighbors. And the end result of blurring is that everything ends up becoming more similar to its neighbors because it's been kind of, the end result has been kind of averaged in with them. And what is something where everything is somewhat similar to its neighbors? It's something with continuity, right? Continuity basically just means, not too many jumps. In other words, if you go to the next one along, it's kind of similar. So blurring something has the effect of making it into a more continuous map. And one thing that actually is present, so although there's probably not like a blurring function built into the brain, one thing that is present in the brain is that nearby neurons tend to excite each other. They tend to be connected to each other. And the result of that is that if I'm a neuron here and I've got a neuron next to me that's kind of firing away, I'm quite likely to fire too. So neurons that are close to each other tend to actually end up responding in similar ways. So you end up with things that are similar to their neighbors, so you end up with smooth maps. So in fact, if you want to build a computational model, and people have done quite a lot of modeling work on this kind of stuff, which makes something that looks like a map, So the term for, the kind of neuroscience jargon term for this is a topographic map, which basically means a kind of smooth map, which represents something out there in the world. So if you want to make something that looks like a topographic map, a good way of doing it is having neurons that actually kind of excite their neighbors and produce nearby similar reactions to each other, and that gives you this property of continuity. And so that's the if it seems like kind of magic that blurring random orientations makes something that looks like an orientation map, it's really because blurring is like a kind of enforcing this smoothness and local similarity, and the brain actually seems to do that too. But of course you can't have perfect continuity because you can't actually, as we discussed a little bit the other day, you can't actually really get a smooth, completely smooth mapping, smooth everywhere mapping of this kind of ring-shaped structure of orientation onto a 2D surface. You're going to have some breaks somewhere. And so that's these kind of things here. So, so the part that's more relevant for fMRI is, let's try chopping this space up into voxels. So, so let's look a little bit at how we actually would do this in Matlab. And this really is extremely similar to the kind of stuff if you actually do, you know, those of you who for your projects are going to be doing analysis of data set, you'll be doing stuff just like this. And even if you're not doing that for your project, we're going to be doing stuff like that in some of the practicals later in the semester anyway. Okay, so we're going to slice up things into different voxels. So how do we do that? So our orientation map is actually, we've called it blurred theta. Remember, theta means orientation. So that's 200 by 200. And there's this nice feature in Matlab where you can kind of float your mouse over stuff and it shows you the structure of things. So then we're going to say, okay, well, how are we going to slice it up into voxels? So in this case, we just happen to choose 4, and you can see that actually in the image. Oops, wrong one. So we've got 4 by 4 here. And what we're going to do is make the, take this 200 by 200 orientation map and chunk it into the contents of each of this 4 by 4 map of voxels. So this is taking a bunch of data and sampling from it at a different resolution. In this case, we're going from a 200 by 200 resolution to a 4 by 4 resolution. And this happens in MRI all the time. This is basically what almost any operation on MRI is. So remember we were talking about in the computer practical recently, we were doing realignment and spatial normalization, and one of the options was reslicing the image. So reslicing the image basically means taking one grid of numbers and turning it into a different grid of numbers. Now, in that particular case, the grid of numbers was the same size grid. It was just kind of shifted around a bit. But actually a normalization where you're taking a brain and you're kind of squishing it onto a template image, it's quite common to change the voxel size. And so that's a kind of resampling onto a grid. And so that's basically what we're going to do now, except it's going to be a very, very coarse resampling because we're going to take a 200 by 200 thing and turn it into a 4 by 4 thing. Okay, so how do you do that in Matlab? So there's different ways, you know, like anything else, there's different ways of doing it. But a kind of easy to understand, but not necessarily the most beautiful or elegant or super duper efficient way of doing it is using for loops. Just a quick question, how many of you have done like any programming of any sort before? Okay, and how many of you like, and there's no shame in this at all, how many of you have just not done any programming at all? Okay, well, everyone's done some programming. Okay, well that's interesting. So everyone's probably, everyone starts off in life not having done some programming. So if any of you happen to be in that state, that's fine. We were all in that state at some point. I think that's a true statement. I mean, you know, there's probably debate about that. So this is a for loop. This is truly elegant. Matlab doesn't have for loops in it. But if you want to make stuff that's that's easy to understand, then sometimes they're useful. Okay, so we're going to take this 200 by 200 thing called blurred theta and chunk it up into this 4 by 4 thing called voxel contents. So first of all, it's often convenient programming to set your thing up full of zeros, because that just kind of makes sure that if you don't accidentally get the stuff that was in it last time you ran your program, things like that. So we're going to have, in this case, we've got a 3-dimensional matrix. So we've got 4 units this way, 4 units this way, and then we've got, we're going to, first of all, record all of the orientations that are present in there. So we're going to record so this thing is, it's 200 across, but we're going to cut it into 4 bits, so it's 50 by 50. So we're going to get 2,500 things in there. We're going to record the value of all of these 2,500 pixels, basically. So we're going to do that. So this thing here, voxel contents, ends up being 4 by 4 by 2,500. So you know how I say it's useful usually not to call your variables, just like A or B. Pretty much the only time when I mean this is a stylistic thing, but the only time probably where you actually, it's kind of okay to call, in my opinion, where it's okay to call your variables as single letters if they're x and y and z coordinates, because you kind of know what they mean. But the killer thing is when you call them like very short names, and then they come back to it 2 weeks later and you cannot for life remember what they mean. And that you kind of have to do that to yourself a few times before you truly appreciate how painful that is. It can be extremely painful. Anyway, although some people find it painful to have variables called things like voxel underscore size, but I personally dislike that. Okay, so we're going to go through the x, going to go through the y, and for every voxel, we're just going to get a copy of all the stuff that's in that, all of the blurred theta stuff, all of this kind of orientation map that's in that particular voxel, and then we end up with this thing that's 4 by 4 by 2,500 that contains all the voxel contents. Then we're going to, this is just a graphical thing that draws those black lines on there, just so you can kind of visualize where the voxels are. But one of the things that's nice about Matlab, I mean, you can do this in other programming languages like R and Python too, but in any of the ones that are kind of friendly to use, it's always easy to plot stuff. Until you can actually plot your data, it's very hard to actually have any idea what's going on. So the simpler it makes it, the simpler the programming language makes it for you to plot stuff, the easier it is for you to kind of get an intuitive handle on what you're doing. So in Matlab, if you want to plot stuff, the command is just called plot. So that's kind of easy. Okay, now what we want to do is we want to take this continuous smooth map and we want to turn it into something which is a more kind of compact representation of what the orientations are in there. In other words, this kind of histogram that says, okay, in this voxel, I got a lot of this orientation, but not very much of this. So this is a very informative voxel here. In this voxel, everything is more kind of flat. So we're going to take this kind of continuous map of 2,500 pixel values inside of each one of these little, inside each one of these simulated voxels, and we're going to make a histogram of it. And again, with being fairly friendly, Matlab actually just lets you do that just using a command called hist for histogram. So what you have to do to make a histogram, histogram is just, in case you know, a histogram is just another way of saying a bar chart which shows the frequency of things falling into different bins. So you have to say, okay, where am I going to put my bins? So in this case, the range to be traversed is 0 to 360 degrees, except we're talking in radians, so it's like 0 to 2 pi. Although it actually turns out to be, well, this is actually a key distinction between being orientation selective and being direction selective. Okay, so remember we talked a little bit about how there's high-level visual regions like MT, which are direction selective, so they're very sensitive to movement. So if you're a direction-sensitive neuron, a line going this way is not the same thing as a line going this way. Okay? But if you're just an orientation-sensitive neuron, a line going this way and a line going this way are the same thing. You're like, yep, it's pointing that way. So if you're a direction-sensitive neuron, there's actually, the world of directions is actually 360 degrees. If you're an orientation-sensitive neuron who's not direction-sensitive, then the world of directions is actually only 180 degrees, because whether it's going this way or that way, it's the same thing. And that's actually a distinction which you can see in the in cortical maps as well. So these maps that we've shown of visual cortex are actually treating this and this as the same way. So so in this case, the range of bins is going from minus pi by 2 to plus pi by 2. So now we're going to go through each of the voxels, and we're going to make a histogram of it, and we're going to see how much orientation stuff is there in each of these voxels. So, in a sense, this is what an actual MRI voxel is doing. An actual MRI voxel has lots and lots and lots of neurons inside it. Lots and lots and lots of very tiny blood capillaries providing oxygen to those neurons. And it just gives you, and the overall MRI signal from that voxel is just a big coarse agglomeration of everything that's in there. So it's basically just saying, it's as if the brain is doing a histogram and just saying, all this stuff that's in here, tell me what I got. So, in fact, actually, what you're even getting is not just stuff that's inside the voxel, but you're getting some stuff that's kind of nearby the voxel as well. You're getting all kinds of things. It's a big and noisy and imperfect measure. Okay, so here's another one of these for loops. So this is the crucial bit here. So we take the voxel contents and we histogram them, saying to what degree do these voxel contents fall into bins centered on these bin centers that we just made. And this is actually a command which again is kind of useful in the world of, it's useful for Matlab in general. It's especially useful in processing MRI. So we've got this thing, we've got this three-dimensional thing here called voxel contents. Okay? And we want to turn it into a one-dimensional thing, which is just how much orientation stuff is there in each one of those voxels. And so in doing that, we're going to get rid of two of the dimensions. And so it often happens that the two dimensions that you want to get rid of, instead of something being, say, 4 by 4 by 2500, you might end up with something that's like 4 by 1 by 2500, or 4 by 4 by 1, or something like that. And so, say something is 4 by 4 by 1, as far as Matlab is concerned, it's a three-dimensional thing, but the third dimension is kind of not really a dimension, because there's only one of them. A 4 by 4 by 1 thing is really a 2D grid, it's not really a 3D grid. So it's computationally convenient to say, yeah, just throw away those empty dimensions. We don't want them. And that's what this thing called squeeze does. Okay, so it literally just says, squeeze out the empty dimensions. And this happens. This is useful for MRI because this happens all the time in MRI. So if you have, say, you have a 3D. We're going to explore doing this later on in the semester. But say you have a 3D MRI image and you want to pull out a particular slice. This is a very, very common thing to want to do. So say you've got, a 64 by 64 by 30 image, which is a very typical kind of size for an fMRI fold image. And you say, give me slice 25. Okay? So then you have the end result will be something that's 64 by 64 by 1, but it's much more convenient to you for the end result to be a two-dimensional thing, namely a slice, than a three-dimensional thing, maybe a slice with this kind of unhelpful little, I have size 1 dimension hanging off the end. and it's even worse if it's in the middle. So so squeeze gets rid of that. So squeeze is just, you know, like, if the people who wrote Matlab were trying to be friendly to MRI people, then they succeeded in doing that when they wrote squeeze. So we end up with a bunch of frequencies of how much is each particular orientation present in that voxel. So if this bunch of frequencies is kind of uniform, then this is going to be one of those uninformative voxels that basically is equally tuned to every single orientation. And if it's not uniform, then we might be able to squeeze a little bit of information out of this voxel. Not very much, so we're going to need to integrate across all the voxels. And the degree to which this voxel has a slight preference to one orientation or another, just because it happened to have more of that orientation stuff in it, then that's a potential source for our classifier to be able to pull out some information. Okay, so we're going to say the degree to which a given voxel is active is the amount for a particular orientation is going to be just the amount of orientation sensitive stuff for that particular orientation that's in that voxel. So that's this thing, voxel activations. So now we've reduced this down from a completely continuous orientation map to 8 different bins. Okay, so now we've got 4x4 grid of voxels, so we have 8 sets of activations, one for each of the different orientations that could be presented. So that's what our voxel activations thing is. So you can see why it can be kind of handy to have a 3-dimensional matrix, even when it's not actually x, y, z space dimensions. In this case, the 2 dimensions are space x, space y, and condition. And this is actually also something that you do a lot in MRI. So you can conveniently have activations for all your different conditions all held together in the same data structure by making condition, you know, the extra dimension. Okay, so now we've got our kind of simulated voxel activations. This stuff just plots that. If you're interested in how to do pretty plots, you can look at that. Okay, so now comes the bit where we're actually going to turn this into something like activation and do something very much similar to classification on the activation. Is any of this clear, by the way, or is this like I'm continually a little unsure, in part because everyone has different backgrounds, and in part just because, you know, it's kind of hard to know how something's coming across. Whether I'm kind of explaining things in like way too much detail or way too little detail, or some combination of way too much detail and way too little detail. My guess is that actually the answer to that is quite dependent upon, you know, how much you've already done Matlab, how much you've actually messed around with classification a little bit. But the only way I can know is if you say, no, I don't, you know, please go over that bit again. And so please don't be shy about doing that, because I'm completely certain that lots of this will not be very familiar to all of you. And this is a lot more kind of computationally detailed than we've really kind of done much so far in this class. So do not be in the tiniest bit alarmed if you think, well, you know, this doesn't seem quite clear to me. Okay, so what happens in an actual fMRI study? What happened in the actual Kamitani and Tong study? Well, in the actual study, what they did was they showed, you know, an orientation, looked at people's activation, showed a different orientation, looked at people's activation, did that for the different orientations. So you show one orientation at a time, looked at the activation patterns across the voxels. So we're going to kind of do that in a simulated sense now. You can ignore this stuff about color maps unless you happen to be super interested in how you play with color maps in Matlab. Okay. So we've got these different orientation bins, in this case 8 of them. And we're going to go through, so we're showing 8 different orientations. We're going to show each orientation, kind of virtually show each orientation one by one, and see what activation that makes across the voxels. And of course, because this is a simulation, the activation that we get in each voxel is going to be just basically how much of that particular orientation is present in that voxel. So if we're showing the orientation that's color-coded as red in this case, which is, it doesn't really matter which one it is, but it happens to be, this kind of vertical-ish one here. So if we're showing so we're going to pretend, okay, now let's pretend we're showing that red orientation. So you can see just intuitively, okay, well this voxel here is going to become quite active. This one here is going to become not very active, and so on. So this orientation is going to induce an orientation, a set of activations, a pattern, a voxel activation pattern across these voxels, just purely dependent upon how much does each voxel happen to include stuff that's tuned to that particular orientation. So if you show red, we're going to kind of expect, if we programmed it right, that there's going to be a lot of activation here and not so much here. If you show the orientation that's kind of color-coded as purple, then it's going to probably be a little more uniform. A lot of these voxels will be quite active, not very much activation up here, things like that. Okay. So this is in a sense, if this theory is right as to what's actually driving the actual activation in the actual Kamitani and Tong study, then this simulation would be kind of capturing some of the essence of that. Okay, so how do you do that in Matlab? So we're going to go through each orientation one by one. There's 8 of them all together. And we're going to say, okay, for this particular orientation, count how much stuff is present in this particular bin that we're looking at. So a bin has a floor and a ceiling, like an upper bound and lower bound. And so we just say, so remember that we stored all our orientations in this thing called blurred theta. So we're going to say, for this particular orientation, give me everything that's bigger than the floor and less than the ceiling. Okay, everything that falls into that bin. Okay, so that's what this does here. These little 3 dots here is, if you've got like a long line in Matlab, then it's convenient to just kind of make it go on to the next line, but you have to tell Matlab that it's continuing on to the next line. That's what this 3 dots does. So this is actually, this line is also, this is kind of more useful from a programming point of view, but if you're trying to program any kind of condition statement, then you'll want to do this kind of thing quite a lot. So remember that the criterion for being in a bin is I'm higher than the floor and I'm less than the ceiling. Okay? So if you want to say, give me all the stuff that's higher than the floor, that's what this top line here does. So this says, blurred theta is all the orientations. This says is great. This means it's greater than or equal to. So remember, this is a 200 by 200 matrix. It's just that kind of big picture that we saw, and this is just a single number. So this top bit here says, return me a 200 by 200 matrix exactly the same size as blurred theta, where every single point in it is a 1 if that value in that 200 by 200 matrix is higher than the floor, and is a 0 if it's not higher than the floor. So kind of computer language for something's true is 1, and computer language for something's false is 0. So if I say blurred theta is greater than or equal to orientation floor, that gives me back a whole bunch of 1s and 0s corresponding to whether or not this statement is true. Okay. But I want stuff that's not only greater than the orientation floor, but is also less than the ceiling. Okay, and so a way of getting an and like that in programming is to just multiply 2 things together. So 2 things, if they're both 1, right? The and means only give me a 1 if they're both 1. Okay, so if you multiply the things together, if they're both 1, you get 1, so that's good. If either of them are 0, then the whole multiplication comes to 0. So that breaks the and. So this asterisk here is multiplication, and the dot thing is MATLAB speak for do it for every single element. There's different ways of multiplying a matrix by another matrix. If you've studied linear algebra, there's actually a thing called matrix multiplication, which kind of involves taking one matrix and turning it sideways and then multiplying it like that. But in this case, we don't want to do that. We literally just want to treat them as maps, so you don't want to do the whole turning sideways thing. So you just element by element multiply them, and that's what this little dot means. Okay, so this, I probably should have put some more comments on here actually to kind of explain what's going on. But so this thing here is actually kind of computer language for make me a map of ones and zeros, make me another map of ones and zeros, and then give me stuff that's one only when both of these things are true, when this and that is true, and that's what the element is. So we've got activated pixels only if you're higher than the floor and you're lower than the ceiling.
Do you put in there what the floor is and what the ceiling is?
Yeah,
Like,
yeah. So that's what's made up here. Yeah,
okay.
exactly. So we defined a whole bunch of bins before, and then we read out, what's the first bin, what's the second bin, what's the ceiling. We made them up here. Yeah, I mean, you can download this and play with it, but yeah, no, you absolutely have to specify what these is. That's absolutely right. Okay, so now we've counted how many activated pixels there are in each voxel. Okay, so now we've actually made something that looks a little bit like voxel activations. Okay? So, so we've gone through each of these, this 4x4 grid of voxels, and we've just said, count how much stuff is there in this voxel for orientation 1, for orientation 2, orientation 3, and the end result is things that look much more like voxel activation maps. So this is actually kind of, I mean, this is just a simulation, but this is actually what a real MRI activation map kind of looks like. It's just a bunch of grayscales, just a bunch of values for different voxels. And if we've done this right, then the brightness of this voxel should correspond to how much of a given orientation is present in that voxel. So let's try and make these more or less the same size. Can you see those different grayscales at the back? Is that shown? Okay, good. So here's orientation 1 corresponding to this one here. And so you can see that this voxel just happens to have a lot of neurons sensitive to that first orientation in it. And so I guess this is working right because that's the most active voxel. And then right next to it, underneath it, there's a voxel with hardly anything in it. And so that's the least active voxel. And then you can see that, for some of the orientations, there's a lot more uniformity. So for this orientation that's color-coded yellow,